Thanks, Liam, for the kind introduction. So today what I'm going to do is show a little bit what we found in terms of geotechnical and geological aspect, but also, although it was not the focus of our reconnaissance, also some structural damage observed during our reconnaissance for the 2016 Kumamoto earthquake in Japan. My name is Gabriele Chiaro, and Gavin is over there. I will start the first part of this presentation, and I will leave it to Gavin to conduct the second part of the presentation. So this is our team, myself, Gavin, Brabha is sitting over there, and also Chris from GNS. And the NZSEE team was joined a team from Japan, and this was one of our lunch on site in Mashigi town, and you can see Professor Yamada and a student from the University of Tokyo and Yamada from the University of Osaka. The outline of our presentation. I will go first through, I will introduce you the Kumamoto earthquake sequence, and then I will talk about general earthquake effect in terms of ground motion, fault rupture, landslides, and liquefaction. And then Gavin will talk about the performance of building infrastructures, focusing on the impact of geotechnical and geological aspect on the performance of such building infrastructures. He will talk about residential housing, retaining walls, bridge, and transportation systems. And we'll finish our talk with some key findings, some relevance for New Zealand, and providing some recommendation from New Zealand practice. So the Kumamoto earthquake sequence, the first earthquake of the sequence happened on the April 14 at 9:26 p.m. and the moment magnitude was 6.2, and the epicenter is located here along the Hinago fault. And it's quite shallow earthquakes. The depth of the epicenter is only 11 kilometers. And this earthquake was followed by several aftershocks, but one of the major aftershock was a magnitude 6 earthquake that occurs just a few hours later, just after midnight on the 15th April. But both this earthquake actually was only 4 shocks of a major earthquake that occurs on April 16 at 1:25 a.m., and which magnitude was 7. And this earthquake, compared with the other two, happened along the Futakawa fault. But also, these 3 earthquakes were all quite shallow, the depth between 7 and 12 kilometers as a focal depth. So I show you the major earthquakes, but here also I want to show you the sequence and number of aftershock occurred just following the major earthquakes. And you can see that while the major main shocks are located in this small area here, the aftershock ran along a very long distance, which is several kilometers, almost 30 kilometers. And one of the major, other major aftershock also happened in this area here and produced several damage. This is typical ground motion recorded by the strong motion system in Japan, the KNET system. The upper one is the accelerogram in Kumamoto city of the first earthquake, of course, in the 14th of April. And also this one is for Mashigi town, also occurs in the same, so for the same event of 14 April. And you can see that in Mashigi town, the acceleration, the horizontal acceleration, north-south direction, east-west acceleration, they have very high peak. In this case, exceed 800 gal. In this case, almost 1,000 gal. But also the vertical acceleration is quite high. In this case, exceeded 1,000 gal. So we have both vertical and horizontal acceleration very, very high. But for the same earthquake in Kumamoto city, which is not that far away, the acceleration is much, much lower. We have probably 500 gals in here in the north-south direction, and around 300 gal only in the east-west direction. But very, very, compared with Mashigi town, much lower vertical acceleration. And the bottom two figures shows the event, the major event occurred on the 16th April, both for the same station, the Kumamoto and Mashiki. You can see now that also in Kumamoto, actually, for the second event, the acceleration is quite high. In terms of, for example, the horizontal peak ground acceleration is almost 900 gal, and in the east-west direction is almost 600 gal. And also in terms of vertical acceleration, we have almost 600 gal, so much more severe earthquake. If you look at the same earthquake recorded in Mashiki town, here again we have a very high acceleration. The horizontal one in east-west direction exceeded 1,000 gal. And also the vertical one now is very close to 1,000 gal. So you can see that in Mashiki town, in both events, the 6.2, magnitude 6 and magnitude 7, we have a very high acceleration. So the first earthquake produced a lot of damage and a collapse of many buildings, but many buildings were also severely damaged, but not fully collapsed. And of course,
you may want to explain what gal represents, because maybe some here are not familiar with the unit of gals.
Okay. So
one gal is 1G.
1G. Yep.
Gal is 1G.
Yep. So in this case, we have over 1G in here, in terms of horizontal stress, and also in terms of vertical acceleration. But also similar value of exceeding 1G were recorded during the second earthquake. And of course, this produced major damage to the already devastated town of Mashiki. So this is the fourth rupture that was observed and was already well known. And you can see that if you look at the ground motion, the shaking map, the highest intensity in terms of damage are recorded in this area here and in this area here. So this area here is basically along the fault and the corridor of the major fault, where we expect and where we record a very large acceleration. But also in here, just outside the major fault, we have very large ground motion. And this case is because we have a basin effect. This is the volcanic caldera of Mount Azo. So in this case, the basin effect induces the amplification of the ground motion. And if you look more in details at the type of hazards we observe on site, we have liquefaction and lateral spreading in this area here around Kumamoto city, and also in Mashiki city here. We have fault rupture and ground shaking in this corridor here mostly. And in this area here where we have the basin effect, we are in the volcanic caldera, we have mostly landslides. So we can say that there are basically three major areas which where three distinct hazards were observed on site. And this is the area we visited during our survey. And so we focus a lot in this area here where a lot of landslides were observed, and we found different type of landslides, and we classified, I will show you later on some, all the type or major type of landslides we have seen. And also we follow different pathway to reach the area where we knew there was some damage. And for example, we visited some area here, Nishihara city, where we could observe the evidence of the fault rupture at the surface, which also damaged a dam, an earth dam. And also here we have evidence, there was clear evidence of the fault rupture. And in Mashiki town, we had a sign of liquefaction. I will show you some image, and as well as in Kumamoto. So our mission was designed in a way that we could over a very large area and see most of the hazards in a very limited amount of time. We were on site only for 7 days. And they were, because the damage and major roads closure, our trip was actually several days. We need, for example, 4 hours to reach a particular site. So it was not easy surveys to plan and to run because there were a lot of constraints. Also, several areas were blocked off because landslide could kill people, and so on. So we need special access in certain areas. And for that reason, we also was very important for us to have colleagues from Japan that could help us in translating and talking with police and other official people and get access. But also was very important to collect information, otherwise all available in Japanese. So one of the major hazards we observed was the fault rupture. And here there is a clear evidence, the photo shows the clear evidence of lateral strike slip. And the displacement, horizontal displacement in this particular location was 1.8 meters. And also if you look map produced by some Japanese colleagues showing the displacement, the blue color in here, for example, this area exceeds 1 meter, is almost 2 meters, movement in this direction, and the upper part, red one, is moving almost 2 meters the opposite direction. So this, the map and the observation are clearly matching each other. So you can imagine this kind of movement induced by the fault, which kind of acceleration induced nearby the fault in the corridor. You can see some houses here damaged. This is also, again, the particular of this earthquake, there was evidence of the fault rupture over about 20 kilometers from here, where there was the epicenter, up to here, where there is the caldera earthquake. So in Nishihara town, which is located in here, the fault passed through an earth dam. At that moment, at the moment of the earthquake, the earth dam was filled by water. And you can see the effect in here, the fault just crossing the dam. And if you look at this figure here, which is just over this sign here, you can see again which kind of devastation the fault induced. In another town, Minami Aso, the fault rupture actually passed through a residential zone, and you can see several buildings here completely tilted. And this is just a close-up of this building here. Again, this is another photo showing the fault rupture here, and you can see all around this area how many houses were damaged. And one thing they did in Japan, all the damaged area were covered by this blue sheet. So you could see in distance how many houses were damaged and in the close distance to the fault. And these houses is a traditional Japanese houses. So they are timber houses, wood houses, and mostly 1 or 2 stories. And the particularity is that they have a very heavy roof. The heavy roof works very well in areas where you have typhoons, very strong winds. But unfortunately, when you have an earthquake, they produce very high inertial forces. That's why, and also this earthquake produced combination very large horizontal and vertical acceleration. And that's why you have most of the houses, the roof was damaged. And also some houses like this house in here was completely destroyed due to the soft story behavior. So I mentioned about landslides, and we were able to identify several types of landslides. And we could classify into earthflow or slides, debris flow, planar translation. Also, we observed a lot of cracks that could eventually produce other landslides during the rainy season or coming earthquakes. Also, we observed large debris avalanches, and also small to medium-sized debris avalanches, and rockfall. So one of the most important earthflow we observed occurred in Minami Aso city, and was occur in a very almost gentle slope. The inclination was only 10%. But you can see that the landslide starting from the crest in here how far could it travel. In this case is almost 600 meters, and here is almost 200 meters, and there is another side here. So it's split in 3 parts. But very importantly, this landslide also invested or hit several houses here, killing 5 people. And here is a close-up of the houses were hit by the landslide. But also the landslide blocked off several important routes. So this is a typical cross-section of the landslide, and the inclination actually is very, very mild, 6 to 7%. So it's not steep at all, but the soil traveled from the crest to the toe over 600 meters. And here there are 2 figures showing a different view of the landslide. In this case, taken from this area here, looking upward, so you can see the crest in here. And this photo here is taken from the crest, looking downward, so you can see the house in here. And very large landslide occur in another mountain area here. I will show you later on more details about this one. We were particularly interested in this landslide because it's a very gentle landslide, but we have a large deformation, extremely large deformation. And once we started to look at this lip failure, we noticed that actually it looks like the soil just slide over a clay surface. But when you look carefully at the surface, you can see some yellowish or orange color material. And we found that this material is pumice soil. And we were able to dig a small trench in collaboration with some Japanese colleagues, and we found that actually this pumice soil is sandwiched between 2 layers of clay. The clay above is volcanic soil, ash volcanic soil, and the bottom one the same. And when we look carefully, actually we noticed that a lot of water was coming through the pumice soil here. So we were able to collect samples, and we wanted to further investigate about the behavior of this material. So is the landslide induced by, triggered by the pumice soil, or for example, is at the interface between the 2 materials? Another important type of landslide we noticed, we could classify, is the debris flow. And this probably is the most important debris flow happening during this earthquake. In here, on the left-hand side, there is a photo taken just after, 1 day after earthquake in April. And you could see how much the mud could enter into the land. And we visited this area almost 3 weeks after the earthquake, and you can see still there is a lot of debris in there. They start already to clean, but still there is a lot of work to be done. But also from these figures in here, so this photo here, you can see that there are houses very, very close to the debris flow also in here. And actually they were hit by the debris flow. So basically the source of debris flow is in here, the upper, the topmost of this mountain here. And if you look the aerial view of this of the debris flow, you can see that it extended over 2 kilometers. And the source is not only localized in one point, but actually there are multi-sources, and they all combine in one major flow, and then eventually this flow hit houses in the valley here. Another important landslide, or type of landslide, is planar translation or slide. And in this particular town, you can see here that we have a sequence of volcanic soil. We have pyroclastic material here. We have a volcanic soil ashes, and then we have a fill material here. So this originally was a rice pad, but it was filled. And then after filling, they built a residential town in here. And nearby the toe of this fill, there is a stream. And what earthquake happened during the earthquake, this fill material moved laterally toward the stream, producing a lot of tension cracks in here, which goes back to several hundred meters. And you can see from this photo that all the houses in this area were completely damaged. I will show also some photo here. This is how it looks like the houses. So very close to the edge of the scarp. So the wood houses, timber houses were damaged, but also reinforced concrete houses was completely tilted, and also the roads and all the lifeline facilities was completely damaged by this kind of landslide. In certain areas, we notice very large tensile cracks present in there. And some of those are extended for 1 meter, so 1 meter gap. And the presence of this crack rings the bell because now, at the time of our survey, there was still aftershock ongoing. And also, the rainy season was approaching. So these cracks are major concern because the water can infiltrate in the cracks and it can create instability of these already unstable slopes. And this is how it looks like, these kind of cracks in here. For example, this area here is the close-up of this area here. But also close here to the crest, you have all the cracks in here. So you have 10 to 12 or maybe 20 meters gap in here, and we have very unstable soil in here. So this potentially could lead more landslides in these areas. So the one I showed before were of small to moderate size, but also we encountered certain landslides of very large volume. For example, this landslide is one of the most famous because it's a landslide that induces the collapse of the most famous bridge in the area, Azure Bridge. And also this landslide also blocked off one of the major highway connecting Oita Prefecture to Kumamoto Prefecture, two large prefecture in the South Island of Japan. But also Minami Aso city was connected to Kumamoto city and all the major infrastructure here, like also an hospital here, through this bridge in here. So you can see from this figure how large is actually the area affected by this landslide. And in here, in this circle here, you can see what is looks like the abutment of the bridge, the highway bridge in there. And this is a typical, is a cross section of the landslide. We have here an average slope is 20 degrees, but if you look carefully, you have that this area here is much steeper. And the bottom, this area here actually was an agricultural terrace area. Is much less steeper. So most of the landslide material or the source comes from this part in here and slides toward the river in here. So in this area, in addition to the very large landslide already shown, there is also minor landslide in this area here. So here you have the river and you have here the scarp. So there was a lot of damage in this area here. Here there is a high voltage tower, and there is a bridge in here, and they were extensively damaged. I will show you more photo later on. So the small to moderate sized debris avalanche occur in this area actually they affect a large area all along this aging here. And for example, they produce the damage of this bridge abutment here, and also the collapse or damage of the road approaching to the bridge in here. but also they produce the failure of other small bridges in this area here. And these figures here is just a close-up of these piers in here. So although this is a small size debris, the impact actually was quite severe because affected many, many important bridges and critical structure in a very limited area. In the same area, also we had a lot of rock falls, and you could see from very small boulders like this to a very large, several meters boulders. And this kind of boulder here also overpass the protection here, and they fall, for example, you can see here, they fall from the upper road into the other road, and they land on cars that were parking in there. Fortunately, it was night time, so nobody was in the cars, but you can see what could be the effect of such a rock fall. But the other important aspect, we found that this kind of rock falls and the entity of rock falls, the amount of rocks, actually had a severe impact also in the protection system. Were designed to resist to smaller boulders, or maybe were designed for, in this case, to resist against static loads induced by the rock. But due to the very large vertical and horizontal displacement of the rocks, actually they could not retain the rocks, and they were severely damaged. This photo is particularly important because it shows a critical aspect of infrastructures in a very limited area. This probably is 1 kilometer by 1 kilometer. So here we have evidence of the fault surface, and I show you some buildings damaged directly impacted by the fault surface rupture. Very close to the fault rupture, we have the very large landslide here, which blocked off the highway, but also induced the full collapse of the very important bridge. Also, we have here a debris flow, which is threatening one of the critical hospital, which was used by people of this town, which now not only cannot access in this area, but also in order to achieve this hospital, they have to travel long distances. Because of this landslide, actually the hospital was temporarily closed at the time of our survey. This area here is the edge of this area here. And you can see how extensive is the area damaged in here. And also you have minor landslides in here, which severely damaged several roads in here, secondary roads. There is also a railway passing this way here, was blocked off by another landslide. And in this area here, there was under construction a new earth dam, and it was and while it was constructed, was severely affected not only by the fault, but also landslide induced by the fault rupture. So you can see that how many critical infrastructures are built in a very limited area, and which was just on the top of rock fracture and fault rupture, and also how was the impact of fault rupture in this area, producing very large acceleration and therefore a lot of landslides. Liquefaction was observed in several areas. It was not one of the major hazards happening during this earthquake, but it was observed in several areas. So it was observed in the port area, but at the time of the survey it was already cleared off, so there was no evidence anymore. But in the Kumamoto city, we were able still to see some effect of liquefaction. For example, here you have evidence of the sand eruption nearby a power line. But also we have clear evidence of subsidence and tilting of bridges, of the buildings. And also in Mashiki town, which was affected by very large acceleration, both vertical and horizontal, was somehow affected by earthquake. In this particular case, there was not much evidence at the surface. There was not much sandy balling at the surface. But there was evidence of subsidence with damage to pipeline and buried pipelines and systems. But also there was evidence of lateral spreading, and most importantly, there was subsidence of the riverbank. And due to the rainy season approaching, one of the countermeasures adopted was to use a large bag of gravel soils and covered by polyethylene to create a temporary countermeasures for the flooding. From now ahead, Gavin will talk about the performance of built infrastructure. Thank you.
There's a whole lot of numbers here. There's a lot of building damage, and Gabriele showed the photos of the houses with the blue tarpaulins on the roofs and some that had collapsed. So out of 90,000 houses that were affected, damaged in some way, 2,500 totally collapsed and 4,000 partially collapsed. This damage was caused by the strong ground shaking close to the epicenter and along the faults, particularly, and we could see that from the blue tarpaulins on the roofs very close to the fault rupture. There's some liquefaction and associated subsidence which contributed to it, and lateral spreading, and there were a large number of houses destroyed by landslides. So going through the various types of infrastructure that was affected, there are a lot of stone walls, unreinforced stone walls in the area we visited, and a lot of those performed very well. Concrete faced but unreinforced walls similarly were very prevalent, and most of those stood up okay. But once they started moving, the gravel behind them would wedge them outwards until eventually they would collapse. Similarly here, large concrete panels, some of them moving on top of each other and some just toppling eventually. Reinforced earth walls. Everyone says they're fantastic in earthquakes, and generally they are. But this is one here which part of it worked all right. This wall had a very high slope above it, and clearly the reinforcement wasn't quite long enough, because there's the reinforcement there being pulled out as the face. The reinforced block collapsed, and that's the view of it from the top, leading this road to be realigned back up the hill away from this mess, which will take some tidying up. Some walls that we noticed that we inferred, certainly this one was the rock that bounced off the top of it. It's very, very light anchors, so we inferred that to be actually a polystyrene fill with the concrete facing, which performed very well. Here's another one. You can see the polystyrene blocks, and I think the fault went through there, which has busted off the concrete facing, but the polystyrene blocks themselves performed okay. Moving on to bridges, some interesting observations. There's the classic settlement of a bridge abutment here, 300 or 400 millimetres of settlement caused by deeper seated liquefaction. Bridge is piled, it's staying where it was. And so the temporary countermeasure is to just build it up with asphaltic concrete. Same bridge, you can see how much settlement there's been of the ground around it. This here is further down this waterway. This is a bridge that used to line up with that, and very hard to see on this slide, but that measurement there is 335. So 335 millimetres is the different distance between the centre of the beam now and the centre of the pad that it was sitting on. So this bridge has been thrown up in the air despite being notionally locked in, and it's landed in a different place. So as a consequence of the strong vertical accelerations in our view. That's not too bad to fix. There's another one that'll be a bit trickier. So moving on to long span steel girder bridges. Here's one similarly through a riverbank, so there's been some settlement. Large vertical accelerations have meant that this bridge is now sitting on, it used to sit on bearing underneath that stiffener. They've had to put the stiffener where the new bearing is. You can see things have moved sideways a little bit as well with this drainage pipe pulling apart. Looking in detail of where it used to be founded, which was on supported on this bearing here, presumably underneath that stiffener. It's now not, so they've got new bearing under here with a new stiffener and more bearing there held on not terribly securely. At the end of the eye girder, the same bridge, there's a stiffening plate here, but there's no end plate on the eye girder, so the eye girder has just punched its way into the back wall of the abutment. So interesting consequences of suboptimal detailing, I'd suggest. Seen some of these before. There's a bridge deck attacked by a rockfall, and the rockfall overwhelmed it in parts. This part's performed fine. This is the Asso Bridge, which was taken up by the very edge of the landslides. An unfortunate sighting, really. If it had been another 100 metres that way, it would have been fine. Bridge here with the dropped abutment. This was an abutment which was probably working quite nicely on this jointed rock mass until the rock mass got shaken apart by the earthquake motion and some topographic amplification and some near-fault effects. And that's the approach to this same bridge. And so the whole approach road has similarly been compromised by concentrated very high accelerations acting on a broken rock mass. For the structural engineers, here's a bridge which has been retrofitted with a damper or some kind of restraint mechanism which wasn't terribly well connected to the existing bridge. So the earthquake will find a weak link, and it found it here. Same bridge, same damper from a different view. Bridge itself seemed fine. This bridge here is a rather cockeyed shot, but this is another eye girder bridge, so like their weathering steel over there. This bridge is 260 metres long, and it's on a curve. And when we walked up it, we walked up the other side, and then we came back and we saw this. So the bridge had been thrown up in the air by the strong vertical accelerations, and it landed up to 1.5 metres off its bearing. At one end it was 1.5 metres offset. And you can see here from this drainage pipe, if it had just been moved sideways without any vertical component, then that would have broken off, but it's been plucked out and dropped down in a different place. So pretty interesting for the bridge guys, I think. Moving on to expressway embankments. This is a reasonably high embankment next to a drainage channel which had collapsed with a classical circular failure mechanism and was being rebuilt. So this was three weeks or so after the earthquake. And the Japanese are very keen on these plastic bags, woven plastic bags filled with gravel, and they use them for everything. They were rebuilding roads on top of these things. They're using them here as a gravity retaining wall, which I think is pretty clever. So the lesson for us is to have a stockpile of these bags and know where to get the gravel from. If it had been me, I would have been putting some cement in the gravel so these could be essentially permanent, and perhaps putting some geogrid in here to reinforce the backfill behind. And you'd be quite happy leaving that in place for 50 or 100 years, I think. Just another view of it. Moving on to the Earth Dam, and Gabriele showed you some photos of this previously. So this is very close to the fault rupture goes through here, so very, very high shaking. That 260 metre long steel bridge is just down the road. So when we looked at this, we didn't walk around it. It had been, the water level had been lowered shortly after the earthquake. There's clearly a lot of damage at where the fault goes through the outflow structure. It wrecked a retaining wall. but there was no catastrophic leakage of this, surprisingly. And the fault rupture was found by other researchers over on that side there as well. But the earth dam at least did its job. And this is in that area of concentrated damage where the earth dam was being built. This is pretty cool. We were there late in the day, and the guys operating these machines were just packing up. And the operators were actually up on here beside us. So these are all remote controlled excavators and bulldozers. They're operated by these robots that you can't really see very well, but they're sitting in the driver's seat with arms, just doing what needs doing. And the operators just pressed a button, and these things lined themselves up and walked back to base. So the operators could knock off early. But we were talking to them, or our Japanese colleagues were talking to them, and they were looking for construction machinery that had been lost in this landslide that had taken out the right abutment of their future dam. It had also taken out the access road down to the base of the river where they were building the dam foundations, and another landslide on the other side had blocked the diversion tunnel that was being excavated as well. So they're pretty much stuffed, and the rainy season's on its way, so I don't quite know how they're going to get out of that. This is a view of that dam site, and Gabriele mentioned the railway line. There's the railway coming over the gorge in a bridge, going into a short tunnel, coming out into a landslide, coming out the other side of the landslide. Here's the various access roads for the dam site, and the guys with the remote control gear were playing around over in here, looking for whatever these white things were. On the edge of this scarp was a tower for a high voltage transmission line, and it's a bit precarious. They actually were in the process of building replacement temporary towers, and so just over here was a tower, full-size tower, and it was founded on steel plates. So they just laid out a whole lot of thick steel plates, stood a tower up, and erected a tower on it, and held it down with more steel plates. So they're pretty well set up. Moving on to social impact briefly. 49 deaths from the earthquakes in total, of which they were really centred in two locations. Minami Aso village, which was a mixture of landslide fatalities and building collapse fatalities, and Mashiki town, which is building collapse fatalities. So the earthquake happened at about 1 in the morning, the main earthquake. That's where these people were tucked up in bed, and the houses let them down, or the ground around them let them down with landslides. 20 deaths afterwards. This was a combination of post-earthquake landslides, destroying more houses, and people dying from complications from being in the evacuation centres in cramped conditions, so DVT type or related deaths. A lot of people ended up in shelters. So 14%, 15% of the population of Kumamoto City, up to in Nishihara village, which is close to that dam, very close to the fault rupture, so very high accelerations. Over 40% of people ended up in emergency accommodation. So we debated the key findings from this trip to bring back to the industry in New Zealand, and there's quite a number of them, and these aren't in any particular order. So I'll just talk through them quickly. Generally, engineering designed structures perform well unless they were attacked by something from off-site, like a landslide. Obviously the vertical component was interesting. The severe damage was concentrated very close to the fault rupture. Earthquakes cause a lot of hazards, and liquefaction is only one of them. So it was interesting for us as New Zealand practitioners and researchers, so conditioned to Christchurch and liquefaction being the main problem, that it isn't always the main problem. It certainly occurred on the alluvial plains outside the caldera, but there was a sufficiently thick crust that the effects were really largely related to settlement and therefore flooding. Quite a lot of landslides initiated very high up on slopes, perhaps as topographic amplification, perhaps contrast in behaviour between the rock and the overlying soil. But on these in steep topography, those landslides pick up a lot of rock and trees and other debris on the way down the hill, and turn into the debris flow that we saw photos of. Relatively gentle slopes can fail in earthquakes if you've got the wrong subsurface geometry, so a water-bearing confined layer which wants to collapse or contract when it's shaken, or even when it just starts to move down the hill. And so that's of interest for people in the volcanic plateau. Hilltop cracking, that's going to be interesting once the rains get into it. The rock slopes that look fine in a static world can shake apart with significant earthquake shaking. And so that can really compromise what's built on them. Small earth failures can have a big consequence if they affect the horizontal infrastructure, particularly roads. And watch out for rainfall after your earthquake. There's more. So again, extreme load cases can cause failure of otherwise well-built or well-designed structures, and this is rock falls landing on top of bridge decks. That particular bridge that collapsed, it was actually offset from the rock face, so a design rock fall would probably have passed quite comfortably underneath it. But what happened in this event was too big for it, too big for the gap. Watch those large vertical accelerations. They seem to be becoming more and more common. They started with Kobe, and now we're getting them almost all the time. And I think there's some logic for having bridges in particular, which are just sitting on bearings, constrained so they're guided to jump upwards and land back down in the same place. Doesn't take much more than 1G vertical to throw something up in the air. Unreinforced concrete facings on cut slopes, they actually performed remarkably well, but once they started letting go, they got wedged out and collapsed. Watch where you put your major routes and infrastructure. Look well beyond the site, looking for landslides and other things that might affect either that structure directly or access to it. Interestingly, a lot of critical infrastructure passed through this gap in the caldera wall, and there's a very good reason for the gap in the caldera wall. It's because there's a fault running through it. So you're kind of damned if you do and you're damned if you don't. The topography was quite attractive. Everything got concentrated there, then the fault actually let go. Bench cut slopes seem to perform pretty well. We didn't show any photos of those, but there was a quarry which where very steep slopes actually stood up quite nicely. Keep a stockpile of bags you can fill up with gravel and wrap with polythene for emergency flood protection. All slope repairs, both slopes underneath roads and above roads, were being repaired with these bags. Yeah, liquefaction didn't have a significant surface expression, but it had certainly happened from the subsidence. So thick enough crusts to prevent sand boils and clear expression. Some people are postulating that perhaps there's an increased liquefaction resistance of volcanically derived alluvial soils, and that's something that people are thinking about in the Waikato as well. But that would more prevent liquefaction, I would have thought, perhaps help to reduce lateral spreading. So relevance for us. Not surprisingly, older houses with poor bracing didn't do very well. Heavy tile roofs don't help. They're good in a typhoon, which you probably get more of than big earthquakes, so it's a bit of a compromise, really. Soft stories let buildings down. There's no surprise there. 10% of the total population of fairly heavily populated area was temporarily evacuated, how would we get on? Where would the Wellington population go? And just consider geohazards when you're locating critical infrastructure, if you can. Often you can't. Land use planning should consider all natural hazards, not just direct fault rupture. We've got guidance from the Ministry for the Environment on avoiding or building close to faults. It should be looking more widely than that. Debris flow hazards on alluvial fans. There's plenty of development on alluvial fans, and they got there by only one reason. And just because we build on them doesn't mean that that mechanism is stopped. Landslides and cracking and future landslides with rain, something to think about. And two catastrophic landslides on relatively flat slopes. Volcanic soils perform well in some places and poorly in others, and leading to failure of these gentle slopes. Post-liquefaction subsidence and potential for flooding. We know about that from Christchurch. We saw it here. Vertically unrestrained bridge structures. Watch vertical accelerations. And you don't always, I've said this, you don't always get liquefaction effects in an earthquake. Recommendations for New Zealand practice. Get the geo-professionals in, and I guess we're all biased, we're all geo-professionals, so we're going to say this anyway. As part of a multidisciplinary team to help with site selection. Think about improving our guidance to practitioners and planners on site selection. Think about our near fault factors in 1170.5 and whether they are giving the right kind of resilience, because we saw a lot of damage located close to faults. Develop guidance for dealing with vertical ground acceleration. It doesn't have to be that expensive, I wouldn't have thought, to guide those bridges straight up and straight down compared to the cost of a bridge. Look into sensitive and unusual soils, and we've got plenty of those in our volcanic regions. And topographic amplification is clearly an issue, and there is research going on into that, and keep it up and get it into practice. Gabriele's just going to wrap up with acknowledgements and question time.
Yeah, we need to think, our team would like to thank a lot of people, especially we receive financial support from NZSEE and our colleague from Japan, the financial support from University of Tokyo. We would like to thank University of Canterbury, Becca, Opus, and JNS, who led our team to carry out the mission. Professor Takashi Kyota, although he could not join our survey, provides vital information on the location and accessibility of the image area. We met with a lot of local authorities and the director of the volcanology laboratory, and they provide us special access to some of the investigation area. We met on site Professor Chigira, Kamai, and Wang from the University of Kyoto, and they assist us to open the trench to retrieve the specimens and encourage us to do further investigation as well. We need to thank Win, Peter, and Quizma that put a lot of efforts and make this this mission possible, and assist us with all the logistics. And last but not least, I would like to thank Misko, Czubranowski, and Rolando Aurense for their recommendation on many aspects of the field reconnaissance. And thank you very much for your kind attention, and if you have any question, we are happy to answer and discuss about that.